Okay, that's different though.
That's like
Those are meant to
eat at like a separate thing. Like slice.
Oh, today.
I got money for slice of bread.
Well, but it can be. It's this week. It's free to go.
Let's do that. I also have $6
I just paid all my utilities and.
All right. Okay. All right. Happy Monday. Okay. Not happy? Aw. What's that?
It's debatable. It's been a long week.
Oh, yeah. Well, there's nothing we can do other than being positive. All right. What's that?
I'm trying to only be negative. Can't be positive. Go ahead.
Have you watched Finding Nemo?
Yes.
Do you know what Dory says? Just keep swimming, swimming, swimming.
Yeah, well,
What do we do? Huh?
It's a little fishy about that.
Okay, meet me after class.
Uh-oh.
All right. Order. Why is it important to, let's talk about protein. Okay. Why is it important to analyze protein content? Yes, Sophie. Yes, because enzyme activity is measured per gram of protein. Good. So maybe properties of proteins are measured based on grams of protein for nutrition. Nutrition claim? Yes. Okay. Yeah, there you go. And quality and standard of identity, all that. Okay, so it's important. So let's start by talking about CalDA. Some of you already did the lab. Some of you will do the lab on Wednesday. But CalDA is one of the oldest, if not the oldest, official method of analyzing protein. It measures amine groups or nitrogen, and then we convert the nitrogen to amount of protein. So it is a chemical reaction, really, and it involves three major steps. First of all, we digest with acid. Second, so first step is digestion. Second is really distillation, but during distillation, neutralization happens. So the acid we neutralize with a base, but really the base we use is in the distillation step. And last is the titration. Throughout these processes, you're going to hear me say, follow the nitrogen. So it's fixing nitrogen in each step, and then we determine nitrogen content. So we follow the nitrogen in all of these three major chemical reactions, and I'll show you the chemical reaction in a little bit. Once we have the nitrogen, we calculate protein by using a conversion factor. So where is this conversion factor coming from? So there is a general conversion factor is 6.25. Where is this 6.25 comes from? The general assumption is that in a protein, you have 16% nitrogen. 16% of the protein is nitrogen. Because in protein made of amino acids, and amino acids have nitrogen or amine groups in them. So the conversion factor becomes 100 over 16 is the 6.25. So it is a crude method of analysis. Why is it crude? Why is determining nitrogen content multiplying it by conversion factor? Yes, Graham.
Other molecules have nitrogen as well.
Yes. What can you name one? Some vitamins have amine groups in them. So some vitamins have nitrogen in them. Nucleic acids have nitrogen in them. So nitrogen exists in certain compounds or molecules. So not all nitrogen in your sample is coming from protein. So when you have nitrogen coming from other sources of protein and you take that conversion factor, assuming that all nitrogen is coming from the protein, this is why it's crude. It's not the true content of your protein, but close as good as, close to. So I don't know if I mention it later or here. Maybe I should mention it here also. Those of you that did the lab, we talked about conversion factors being different for different proteins. So conversion factor for cheese is 6.38, for example. I don't expect you to memorize this. I will tell you in an exam. Wheat gluten is 5.7. So why is that? Why cheese, the conversion factor is different? There are different amino acids in the protein. And do you know which are the 3 basic amino acids among your 22 amino acids? What are the 3 basic amino acids that you learned? Any? 1. Yes. Asparagine is not actually, asparagine converts to aspartic acid, so that's acidic. Glycine? Glycine is no, so smallest amino acid. No, but thank you. I mean, you know, so that's the positivity. Keep swimming.
Is it alanine?
No.
The small?
Tyrosine, no, we know all the amino acids. I love this. Okay.
Lysine.
What?
Lysine.
Oh my gosh, over +3. +3. Dude. Yes, lysine. What? Okay, I'm not gonna ask what else. Do you know what else? Huh? No.
Oh, sorry.
Huh?
It's,
Histidine? One more?
was it serine?
No? You knew them all. Arginine. So lysine, histidine, arginine. Why do I care? Why am I asking about those 3? Because they have extra amine group in their molecule. So you in every amino acid you have an amine group and a carboxyl. Lysine, arginine, and histidine have additional amine groups in them. Also, asparagine does have an extra amine group. Alicia, you said asparagine. It does have an extra amine group in its R chain. So all of these amino acids that have extra amine groups in their R chain causes this per 16% to increase, to be high. So when the 16 is 17 or 18, your conversion factor becomes lower. And if you have less of these amino acids in general, your percent nitrogen will be lower, so your conversion factor will be high. So cheese, for example, has less total nitrogen than wheat, has more total nitrogen in its composition. So that's why wheat, the conversion factor is lower than cheese. Okay, just because it's 100 over the percent of the nitrogen. Okay, so that's why different food products have different conversion factors. But in general, if we don't know, or if it's a food with a mixture of proteins from different sources, we always use the 6.25 as a general kind of factor. Also, ingredient companies that sell protein ingredients, no matter what, they like to bump up their protein content. So even if the conversion factor is 5.17, they use 6.25 so that they can claim higher. They're legal, can't do anything about it, but they're claiming higher protein content than actually is. Okay, so that's that. Moving on to your wonderful chemistry. I love Keldal. I spent 2 years in my master's degree doing Keldal. I'm known to cause disaster, so I'll tell you a story later. Anyway, so the first step is digestion. So you put your sample with a concentrated H2SO4. We add a catalyst. The catalysts have copper in it and potassium sulfate. So it's a combination of specific salts. These salts increase the boiling point of sulfuric acid. Why is it important to increase the boiling point of sulfuric acid? Because then we can digest at higher temperature and not lose the acid during the digestion. So the catalysts speed up the reaction, by definition, they're catalysts. So they speed up the reaction and prevent the sulfuric acid from evaporating too fast by increasing the boiling point. This is one of your questions on your lab report when the roles of the different reagents we look. So what does sulfuric acid with heat and catalyst do? It digests the sample, convert everything into fumes, everything evaporates. CO2, H2O vapor, SO2, sulfur coming from your protein. However, the nitrogen, look in red, we are fixing the nitrogen. We are following the nitrogen. So the nitrogen is fixed as ammonium sulfate. You have NH groups, amine groups in your protein. These amine groups are going to react with the sulfate from the H2SO4, form ammonium sulfate and stay in solution. That ammonium sulfate will stay in solution. Everything else are fumes. And they leave the system, and now you end up with an acid and ammonium sulfate dispersed in that acid and your catalyst, which you don't care about. So the next step is distillation and neutralization. Neutralization happens because you have concentrated acid and we add NOH. So it kind of neutralizes the acid, but the NOH has an important role as well, not just neutralizing the acid, but the sodium and will react with the sulfate, give you sodium sulfate, we don't care, but then it will release ammonia gas. So NH3 now is your nitrogen is in the form of ammonia gas. So NH3 is now your fixed nitrogen that evaporates with water, because the system has water as well. So your ammonia and the water evaporates and get distilled. So there will be a distillation step. They get distilled into a container that has boric acid. So boric acid capture your nitrogen and form ammonium borate. Again, in red, we are following the nitrogen. So we go from ammonium sulfate to ammonia that evaporates and get distilled, captured by boric acid, and now you got ammonium borate. So that borate solution is basic now. We went from acidic to basic. The last step, you titrate with an acid in the presence of, what's the indicator? Methyl red. So in the presence of methyl red, the color changes when you get neutralization or at equilibrium. All of your ammonium borate get titrated and you bring back boric acid. You start with boric acid that captured, I have this. You start with boric acid that captured your nitrogen into ammonium borate. That's basic now. You titrate with HCl to bring back boric acid. But what do we care? Number of moles of ammonia or ammonium ion equal number of moles of borate or borate ion. So the borate plus acid gives you back boric acid. So 1 mole, and 1 mole of acid. So at equilibrium, number of moles of HCl equal number of moles of borate equal number of moles of ammonium, and you have 1 nitrogen, so equal number of moles of nitrogen. Wonderful chemistry. But I will walk you through all that calculation in a little bit. What I want you to know, to remember, there's digestion with strong acid. There's distillation with NOH to capture the ammonia. And then the ammonia is captured by boric acid and then titrated by ooze. So the N is followed. And using the equilibrium equation, we can calculate percent nitrogen. I'll walk you through that equation in a little bit. So this is what we have in the lab. We have a digestion unit where you put your sample in those tubes, you add your catalyst, you add your H2SO4 concentrated, and then you bring this down and you turn on the hot plate at really high temperature. What is the temperature? 420 degrees C, very high temperature. So the catalyst help prevent the H2SO4 from evaporating too fast. And then we have an exhaust system. So it's a closed system because you don't want the fuel to come out. It's not good for you. So the fumes are captured, exhausted into a place where you neutralize the acid and capture any CO2 and SO2 fumes that come out. You'll see that in the lab. What remains after digestion, you have the acid, you have the ammonium sulfate, and the residual catalyst. You take that out, you cool, you add water, and then that part now gets to be on the distillation unit. So the distillation unit, you have steam, generated steam for heat. You add NOH, you dispense NOH into this nice blue color, blue because of the copper catalyst. So you dispense your NOH, the steam is turned on, it starts boiling, water and ammonia are released. They go through the distillation tube here, get distilled. There is a tube that you can see very well. It goes, the ammonia and your water goes through the tube, and the tube is immersed in boric acid. Actually, it's yellow, the boric acid we use. Well, not yellow, right? It's no, it's not yellow. What was it? You put methyl red in, the boric acid turns pink. And then when the ammonia is captured, the color turns yellow. And then you titrate with HCl back to pink. All right, so this is just, there are different types of indicators that people use, but our indicator is methyl red. Okay, so after this is, the distillation is done, you take that and you titrate with HCl back to pink color, and that would be at equilibrium or neutralization, number of moles of acid equal number of moles of borate equal number of moles of nitrogen. So this kind of like shows the ammonia that gets released and captured by your boric acid that has methyl red in it. Okay, any questions? This is the unit I used when I was a graduate student. It's terrible. It's very old, but does the trick. It's digestion and distillation at the same time. So you digest using those big round flasks, and then you have exhaust system that sometimes does not work. And then after you digest, there are the top chambers where you do the distillation after you add your NOH, water and NOH. And then at the bottom, you have tubes where you put the boric acid flask in the back and you collect the ammonia. Now, it looks really shady. Shady, I said. And one time I was digesting a lot of samples, and it was on the top floor and my lab was on the bottom floor. So I put the samples in, went down to my lab, and I just went up to check, and the whole hallway was filled with fume, like white cloud. And all I saw, there was a very tall professor. All I saw is a head above the cloud walking to me and yelling at me, that, what have you done? So we're suffocating here. Well, I don't know. The exhaust stopped working. It wasn't my fault, but well, the story is exhaust system should work. You should check it. And if it doesn't work, you shouldn't do digestion, right, Andressa? Yeah. How many months did it take to fix that exhaust system? Remember we had issues, or weren't you involved in it? Yeah. So we shouldn't digest any samples without making sure that the exhaust system is working because of the fume. All right. So the last step is I'm going to talk about is the calculation. So I will walk you through the calculation. It's easy to memorize this equation because in exam I might tell you, here are your, I'll give you an example to solve. Here are your given and calculate protein. So you want to know this equation. But I like always derive the equation so that you know where each number comes from and why we are using it. So I will walk you through the derivation of this equation. And it would be the basis for a lot of equations later on in other chapters. So equilibrium is what you want to remember in a chemical reaction. You always have, when you're titrating, you reach equilibrium. So it's base, you're titrating with acid to neutralize and reach an equilibrium. And this is the case. When we have ammonia reacting with boric acid, you're going to get ammonium borate. So you take that ammonium borate, which is now base, titrated with HCl, back to boric acid in the presence of methyl red. So at equilibrium, what do we have? So at equilibrium, when you are done titration and you got to that faint pink color, so number of moles of HCl equal number of moles of what at equilibrium? What do you see in the equation? Number of moles of HCl equal number of moles of, before nitrogen, of borate, right? Of borate. Because the borate is the salt that reacts with the H to give you boric acid. So equals numbers of moles, because 1 to 1. So equal number of moles of borate. But with borate, I have ammonia, but 1 mole. So equals number of moles of borate equals number of moles of nitrogen. Yeah, you all following? Do you want me to repeat? We good? Do you want me to repeat? Anybody? Number of moles of HCl equal number of moles of borate equal number of moles of nitrogen. Because 1 mole reacts with 1 mole. Borate, 1 mole reacting with 1 mole of acid. And also you have 1 mole of nitrogen. Okay, so this is at equilibrium. Number of moles equal molarity times volume. We'll get to that, okay? Number of moles also equals mass in grams over molecular weight, grams per mole. So N is for number of moles, okay? moles. So at equilibrium, M by V, I have the molarity of HCl equal to the normality. So I have the molarity of HCl or the normality of HCl. I also have the titration volume, right? So I'm titrating, so I can determine the volume that I'm using to get to that pink color. So I have my molarity or normality, and I have the volume. And it's corrected volume because we also titrate the black. So your volume that you use to titrate the sample minus volume of the black. Okay, so that's your corrected volume. All right, so this, if I say this is number of moles of nitrogen times molarity equal molarity times volume for HCl. Okay, so at equilibrium, number of moles of HCl equal number of moles of borate equal number of moles of nitrogen. Are we all following? A number of moles equals molarity times volume, and number of moles equals mass over molecular weight. So if I say this region is for the nitrogen, and this is for the HCl at equilibrium, this is equal to that. Then I want to solve for the mass of nitrogen. Okay, then I bring this over here. So mass of nitrogen in grams equal the molarity or normality of HCl, that's mole per liter, that's your unit, times volume, usually you titrate in milliliter. If I want to convert this milliliter to liter, what do I need to divide by? By 1,000. So now my units will cancel, because now this becomes in liter. All right, so now molarity is a given. The corrected volume I can get. I want to get the molecular weight of nitrogen, and that's 14. So 14 grams per mole. So now mole cancel. So I want percent nitrogen, grams in 100 grams. So it's the molarity times volume in milliliter times 14. But now I'm not going to worry about the unit for a second so that I don't crowd it. 1,000 times the weight of the sample. Now it's grams per 100 grams. So I need the weight of sample. So that would be in grams. Okay, let me put the units. Grams per mole. And per milliliter, well, liter now. Yeah, so, and then this is moles per liter. Here's liter because we corrected. So liter, moles, times 100. So that's that. This equation at the bottom is that equation top. Question. Okay. Let's solve this. Take a piece of paper for class 2. And take a few minutes to solve this. You have all the given you need. You have 2 replications. So find percent nitrogen for each rep separately. And then get the average of the rep.
Yes.
Okay, anybody with an answer? Did you reach an answer, Kendall? No? Well, even if you applied this, you don't reach an answer? You have all the given to calculate nitrogen.
Oh.
So you just apply, what's the normality of HCl? 0.1142. What's the corrected volume for rep 1? 22 minus 0.2, so that's 21.8, right? All right. You have the 14 grams per mole for nitrogen. You divide by 1,000, multiply by 100, and the gram for rep 1 is 1.015. What is the percent nitrogen? What is the,
I got 3.4.
you got, let me see what you got. 3.43 for rep 1. Very good. What's for rep 2?
3.4.
All right. So you got 3.498. Yes. Okay. So I see what I did here. Okay. And then you calculate the conversion factor. What's the conversion factor for nitrogen? It's in the given. So it says then that protein contains 17.5% nitrogen. So what is the conversion factor? 100 over 17.5. I gave you in this case the percentage of nitrogen expected in the protein. So my conversion factor is 100 over 17.5.
Sorry.
So here, what I'm saying is 17.5 grams of nitrogen in 100 grams of that protein. So if I have 100 grams of protein, 17.5 of it is nitrogen. So the conversion factor that I would use if I have a nitrogen to convert to protein is 100 over 17.5. Right? So what is the conversion factor?
5.7.
Okay, so then you would use that conversion factor to multiply it by your percent nitrogen to get your percent protein for rep 1, 19.62, and rep 2, 19.87. Then you average that. So this would be on wet basis. How do I convert? Or is this on dry basis? What was the question? A dehydrated. Okay, so it's already dried for you. So the answer is on dry basis. Now you have the moisture content is 8% of a pre-dried sample that did before drying. So how would you calculate moisture on a protein on wet basis? You have a dried sample and the original moisture content is 8. How would you convert dry to wet? Yes, Taylor.
5% protein by 92%.
Yes. So you want to calculate on original weight. So it is, you subtract the moisture from 100 and then you multiply that by the protein content on dry bases, and you divide by 100. So to make sure that you did that correctly, dry bases is always higher. The ratio to dry matter is always higher than the percentage on as-is bases. Have any questions? All right. Moving on. Good. All right, so the next method for another official method of analysis, it's also a crude method because again, it's based on nitrogen content. So here, what you do, it's the Dumas method is a nitrogen combustion method. It's automated. It's fully automated. You only weigh your sample. That's all what you do technically, but there's more to it. It's a very demanding equipment. This is the picture of an older LiPo equipment we have. Now our equipment is fancier. You'll see it in the lab. But the principle is the same, really. So what you do is you weigh your sample, and you can weigh multiple samples. We have a crucible. Well, not a crucible, so a rotating head, what do we call it? Carousel, not a crucible. So we have a carousel, and you use either tin foil, a little tin foil you put the sample in, or what is the other one? The gel capsule. Depending on the type of sample, whether it is liquid sample or solid sample. And you weigh your about 0.1 gram plus or minus of your sample in these little sample holders, and you put them, you drop each one of them into a place in the carousel. So, and then it's automated. The equipment drops each sample into a combustion unit. So you have gases, you have air or oxygen. Oxygen, yeah. So you have oxygen gas to help with igniting or increasing the temperature, and also mixing the sample gases with oxygen. But what happens is when you put your sample, and I think it's combusted at really high temperature, probably 950 degrees or something like that. Yeah. So it combusts, and what happens, everything is now in the gaseous form. So CO2, H2O, NO2, NOx. So everything is in the gaseous form. And those are carried with oxygen to something we call the ballast at the back that holds all these gases. And from there, they go into scrubbers. So the scrubbers capture moisture and CO2. Scrubbers over there that capture moisture and CO2. And then the sample passes through a compartment where nitrogen NO gets reduced by copper to N2 gas. So we're converting the NOx into nitrogen gas. The nitrogen gas will go through to the conductivity detector, thermal conductivity detector, similar to the conductivity detector we use in a GC, for example. Sometimes the nitrogen combustion unit has like a column, like in GC, separating the gases. But our unit, we don't have that column. We only have scrubbers. That's why this is grayed out for you. We have scrubbers that scrubs off other gases, and then only nitrogen gas reaches the detector, and you measure change in conductivity with the helium as a carrier gas. So, right, our gas is helium. Okay, you can use different gases, but our gas is helium. carrier inert gas. So basically, we have the combustion. The gases go into the ballast mixed with oxygen. Then they go into first scrubber to remove moisture, and then they get mixed. Another set of scrubbers to remove CO2 and H2O. So that's scrubbers, and then reduction place that got reduced to N2, and then they go into the detection by thermal conductivity. It's few minutes, depending on the unit. It's anywhere between 2 to 4 minutes per sample. So if I want to compare Keldal to Dumas, so are they both based on nitrogen content? So both are based on measuring nitrogen content, but one we use chemical reactions, the other is automated and combustion. So the LICO or the Dumas method using a nitrogen analyzer, the company is LICO, the most common one. It's very expensive and high maintenance. So if we have a lot of samples that we want to run, it makes more sense to have the nitrogen combustion. If we have usually few samples to run, Keldal is cheaper and can be run with fewer samples. Of course, the nitrogen combustion takes less time. If it is calibrated well and it's functioning and it doesn't need maintenance, it's very fast, high throughput. A lot of samples can be analyzed in a short period of time. No chemicals are involved, so technically it's safer than Keldal. But both methods are official methods of analysis. Depending on the type of food, one might be a little bit more accurate than the other, because Keldal, for example, only follows the amine groups, okay? Whereas the Dumas, any nitrogen, not necessarily an amine group, can be detected. Okay, so based on the type of food, Keldal might be a little bit more accurate, but in general, both are accurate and both are very, very precise if you know how to titrate. So you shouldn't have issues. So with that, I'll stop here. Next time, I will finish the last bit of the protein and start carbohydrate. All right. See you later. I saw you get scrubbed off as well. That's the answer, Rob, if you're still here with us. Okay.